Okay, so welcome to the second lecture. As I mentioned at the beginning, the focus of the whole lectures will be heat work conversion. But the main focus of this particular lecture will be energy dissipation. And let's start with the recall of the concepts of heat and work. We already spoke in last lecture about the first law. This is precisely the way we presented it, that we have a system which contains some internal energy, and it's in contact with the thermal bath, and at the same time is operated with some control parameters which operate in time. And we can identify two types of changes of the internal energy. One is identified as work, which is the one which is due to the changes of these control parameters, and the changes in the internal energy which are due to exchanges with the thermal bath are the ones which are identified as heat. Sorry. Yeah. So we are going to work a bit about this idea. Something is happening. Okay. Let's think first in terms of quasi-static processes. So quasi-static processes means that in spite of the fact that these control parameters change in time, we are going to think in terms of snapshots, so several sequences of equilibrium processes that take place for fixed values of these control parameters as they evolve in time. So in general, we will have some Hamiltonian for this system, which will look like this. We will have some Hamiltonian for the bath, some Hamiltonian for the system, which is a function. It depends on these control parameters, and here is where the time dependence comes. And some Hamiltonian which describes the contact between the two systems. An easy situation takes place when the contact between this system and bath is very weak. So let's start in this situation. So we have this contact Hamiltonian, which is basically, we can make it vanishing or very, very small. And we will think, as I said, as a sequence of several equilibrium processes corresponding to frozen values of the control parameters. So the state of our system, of our combined system, will be basically well described by this direct product of the state of the system and the state of the bath. Both of them will contain the same temperature, which is set by the bath. Okay, so this is simple. And now we will express at the given time the internal energy of the system in this way. So we can trace out as the contact is very weak, and we are describing the combined state as a product of these two states for the system of the bath. We can trace out the bath, and the internal energy will be given by this expression. So let's implement changes in this internal energy. As I said, in two ways, by changing the state and by changing the control parameters in a very small interval of time. And we will have these two terms. The first one is the one which is identified as heat, and the second one is the one which is identified as work. To further support the fact that the first term can be identified by heat, we can go to directly calculate. So something happens to move. Okay. So we can go to directly calculate the change in the entropy under this process. And the change of the entropy, so we start with the von Neumann entropy. Here it's not indicated, but I put in the Boltzmann constant equal to 1. So this is the Boltzmann entropy. Let's focus in a situation where there is no exchange of particles, and we can characterize our system simply with this state without including any chemical potential. So just to make life simple. And so we can proceed doing all these calculations for this change in the entropy. So the total change in the entropy, we can proceed. We can substitute here this log rho by the explicit expression and calculate all these derivatives in order to verify at the end that in fact the change in the entropy for these small changes can be written in this way. So this is basically beta and the trace of the change in the state times the Hamiltonian. If we move this beta, so we move this, we substitute beta by 1 over t, and we move it to the other side, we will, it is written explicitly here, and I'm here recovering the Boltzmann constant. So it will happen that in sometimes I'll put Boltzmann constant equal to 1, and also h bar equal to 1, and in the situations where they are important, I'll recover them in the final expressions. This is one example. So here I worked without putting Boltzmann constant equal to 1, and then I recovered here in the final expression the Boltzmann constant, and we see that we precisely recover the interpretation of heat I given before. Okay, so now this is easy. This is, I think most of you have seen this calculation in lectures in your career. But now let's move to the finite time processes. So let's now include the fact that these changes in the control parameters take place in time. So we move to some non-equilibrium situation. As I said in my first lecture, I won't move too far from equilibrium because I want to make contact with thermodynamics. So now we will start thinking in terms of fluxes and the work and in terms of power developed by the forces induced by the changes in time of the external parameters. This definition of the heat flux was already given in the previous lecture. So the heat flux, the best way to, so the most convenient way to define the heat flux is looking at the reservoir and see what happens at the reservoir. So the heat flux is defined without doubt as the change of the change in time of the energy that is stored in the reservoir. And it is something that has to be calculated, as I said in the previous lecture. Now we are going to also introduce the power. So the power takes into account precisely the change in the energy, so the energy stored in the system, but as a response to the external parameters. As the Hamiltonian changes in time as a function of changes in time because the control parameters change in time, we can express this explicit derivative in time in this way, as the derivative of the Hamiltonian with respect to the external parameters times the rate of change of in time of the external parameters. So this quantity here, which is defined here, is given the name of force. And you see that it's a convenient name because you see in this expression that you have a power written as a product of a force times a velocity. So this can be interpreted as a velocity. And the name of force was introduced by Berry. This is an old article by Berry where this concept was used, and he used to define things in terms of forces. So these are definitions. What is important here, before moving further, is the fact that all these quantities, so this is a quantity that depends on the Hamiltonian, depends on the contacts between the bath and the Hamiltonian for the system, depends on many things, but this is a quantity which is an operator. So we have to take a mean value of an operator out of equilibrium, and the power written in this way contains this force, and this force is also an operator. So the strategy now will be to calculate these operators within some approximation out of equilibrium. Yeah, this is precisely what is written here. We have all this Hamiltonian, and for the moment I'll focus on the force. So the force can be, so this is the definition, this is a shorter notation. But the strategy will be to split this force into two components. One component, which is, and I'm going to do the same for the heat flux later, but the first component is the component that is evaluated with the Hamiltonian, with the frozen Hamiltonian. So this is the component that corresponds to a description that is quasi-static, that I'm changing the parameters, making a snapshot and of the values at the time t. And these are basically a sequence of several equilibrium processes defined by the values, the Hamiltonian, evaluated with the values of the parameters at different times. And all the non-equilibrium part is contained in this second component, and this is the difficult part. So this is the state precisely corresponding to the frozen Hamiltonian. Okay, we have at hand linear response theory. So we have usual linear response theory. I'm going to recap briefly. The idea of a linear response is that we have a Hamiltonian which is time dependent and can be split into two terms, one which is non-time dependent and all the time dependent effects are in this other component, which is named H prime. And let's assume for a while that it starts at the given time t0. So if we want to evaluate the any mean value of any observable at any time before this perturbation is connected, is switched on, we know how to do it. And we have this state corresponding to the system in equilibrium. So in equilibrium with the Hamiltonian H0. So the assumption of a linear response is that after this interaction, time-dependent interaction, is connected, we can evaluate the Hamiltonians, the observables, the mean values of the observables as a function of time in this way. We have the same weights as before, as with the Hamiltonian H0, but the states evolve in time. And this is precisely the situation. We have an equilibrium state. We go to some non-equilibrium state. In the equilibrium state previous to the switching on of the time-dependent interaction, states were distributed according to a Boltzmann distribution. Afterwards, it is assumed that states evolve preserving the same distribution. So this is the procedure. So we have to now calculate which is the evolution of the states. This is the evolution in the Schrödinger representation. It is convenient to move to the interaction representation. This is the change, and we know that what all we need to solve in the interaction representation is to solve the evolution of the evolution operator. We have this solution, this formal solution of the evolution operator. This is some difficult problem, but linear response corresponds to approximating this at linear order. So we keep from this exponential, sorry, there is an exponential missing here, sorry, this is exp. From this exponential, we keep only the linear term. So there is some exp missing here. Okay. Now we plug in the calculation of the mean value of the observables, and we end with this expression where we have here the first term, which is the mean value of the observable evaluated with the unperturbed Hamiltonian, and the correction, so the effect of the time-dependent part, which appears in the form of a susceptibility. So what appears there receives the name of a Kubo susceptibility. And we can afterwards think that this T0 at which the time-dependent perturbation is connected can be sent to minus infinity for convenience, because if we want to describe the long time behaviors of the behavior of this observable at times which are much later than the time T0 at which the interaction was connected, we can simply send this T0 to minus infinity. Of course, this is something, some approximation, which is going to be valid if the amplitudes included in this Hamiltonian, in this perturbed Hamiltonian, are small enough. These are what allows me to keep only the first order of this expansion. Okay, so this is just to keep this in mind. So I'm going to do something slightly different, but with following a similar philosophy. So as I said, we have all this Hamiltonian, and we have what we want to do is to split it in some mean value, which is evaluated with the Hamiltonian frozen at the given time, and introduce some linear response for this other part. So it's different from the Kubo that we are always evaluating the unperturbed the quantity that appears here in Kubo is the Hamiltonian without any time-dependent interactions. So now I want to do something different. I want to keep the time-dependent part in the Hamiltonian, but I'll consider it frozen to evaluate this first component, and this other component will be calculated with some linear response way similar to Kubo. I'll explain you. Yeah. So in the Kubo formalism, the Hamiltonian which is going to play the role of H0 is the Hamiltonian with the corresponding to the frozen parameter, so the Hamiltonian frozen at the time t. And we will consider departures of that Hamiltonian. We will introduce perturbations and represent these perturbations as expansions of the Hamiltonian with respect to the time at which I freeze the system. So the perturbation will be expressed in this way. So this is the basically is like a linear order expansion of the time-dependent Hamiltonian, in which the part that plays the role of my H0 in the Kubo language is the first term of the expansion, and the next term of the expansion is this one, which contains the derivative of the, so I'm evaluating the Hamiltonian at the given time t prime as the derivative of the Hamiltonian with respect to the time-dependent parameters times the velocities of the time-dependent parameters evaluated at the time t at which I freeze times t prime minus t. So now this is my perturbation in the Kubo formalism. And afterwards, I proceed as in Kubo. I start from the evolution operator, the full evolution operator. Now these forces are expressed in the Heisenberg, so this is important. So the quantities that appear in Kubo are the operators are expressed in the Heisenberg representation with respect to H0. In our case, our H0 is the frozen Hamiltonian. So all these operators, in particular this operator if, is evaluated in the Heisenberg representation with respect to the frozen Hamiltonian. Okay? I forgot to mention, so there is another version of this which was formulated for closed systems. But the idea is very similar. Now, in this linear response, in this adiabatic linear response, we have the following expressions for the mean value of the observables at a given time t. We have a first component, which corresponds to the frozen component, plus this, which is similar to the susceptibility, but we call it the adiabatic susceptibility, because the usual Kubo susceptibility doesn't contain this t minus t prime. But basically, we have in this way an expansion, a linear response, and linear expansion in the velocities. So we have the frozen term plus some correction, which is described as the rate of change is proportional to the rate of change at which the parameters change in time. This is as usual, we can send this T0 at which this perturbation is connected at T minus infinity. And we have this definition for the adiabatic susceptibility, the thing that enters here. Which is related to Kubo susceptibility. If we introduce the Fourier representation here, it is quite simple to prove that the relation between this susceptibility and Kubo susceptibility is this one. So it's, this is the usual Kubo susceptibility. This is the imaginary time, and this limit at omega going to 0 gives us the adiabatic susceptibility. Okay, so we have this linear expansion. And now some comments. It is important, as in Kubo, I said that it was valid to do that expansion if the amplitude of the perturbations, so of the time-dependent terms, are small. In our case, we introduce some expansion in time. So in order to be valid, that expansion, we need that, and in that expansion in time, so I can go back. Yeah. In that expansion with time, we have this time difference here and these velocities. And this is what enter in the evolution of the mean values of the observables. So in order to be valid, this expansion, we need that these velocities are small enough to behave all this quantity as a perturbation. And this is something that typically happens when the rate of change of the time-dependent parameters, so that when the time scale for the change of the time-dependent parameters is much larger than the typical time scale for the dynamics, internal dynamics of the system. So if the internal dynamics of the system is fast, so the typical rate the typical time for these changes will be small, so these velocities will be small, and this justifies the linear response. So this particular linear response treatment. Okay, so this is the first important comment. The second comment was already mentioned. It can be expressed in terms of Kubo susceptibilities. What is very important is all these quantities are evaluated with respect to the state, this state corresponding to the frozen Hamiltonian, and this is an equilibrium state. So all these susceptibilities obey micro-reversibility, so they also obey Onsager relations. Another appealing feature is that there are several analytical and numerical methods for many body systems to calculate Kubo susceptibilities. And this is a way to use the Kubo susceptibilities to calculate this adiabatic dynamics which could be used to calculate the adiabatic dynamics in many body systems out of equilibrium. So this is something which is, I'll give you an example towards the end of the lecture. So in summary, we introduced the following adiabatic expansion for the observables, which implies this decomposition. Frozen mean values plus some correction which is proportional to the velocities. And we can, in particular, introduce this expansion for the forces and for the fluxes. As I said, these are observables, and we can use that. In the case of the fluxes, we know that if we have just one bath, this is the situation for today, we have just one bath and one system which changes with parameters changing in time, so the flux will be 0 for the frozen component. But we will have this adiabatic correction. Okay, so we are now in the position to identify the two important components of the power. So this is the definition of the power was the force times the velocity. And if I introduce that decomposition, this adiabatic decomposition in the definition of the power, I'll get this expression. We will have some first term, which is the force evaluated with the frozen Hamiltonian times the velocity, plus this other term, which is bilinear in the velocities. So we have these adiabatic coefficients, which, as I mentioned, obey the Onsager relations, and multiplied by two velocities. And so if I focus on these two components, I will see that they behave very differently. So the first component can be identified as a conservative component, as a conservative force, because in fact, if I evaluate the work between 2 points of a given protocol, I see that so this x dot times dt can be expressed as a change in the parameter space. So this is the typical thing we have for conservative forces. So we end in some expression, some integral that depends on the final points of the trajectory. And in particular, if I evaluate this component and I calculate this work in a cycle, as in a cycle I start and I finish at the same point, I will find that this work is equal to 0 as the work done by conservative forces. Instead, this other part is the one which describes the dissipation. So we are arriving at the point of this lecture. This point contains is bilinear and depends on all the details of the trajectory. So this is the component that precisely describes the work that is done by these time-dependent forces and is dissipated in the bath. And if we look at the bath, at the flux entering the bath, and we introduce there this adiabatic expansion, we will have the following. As we said before, this component should be 0 because these are sequence of equilibrium processes at different values of the parameters. And we will have this this adiabatic correction. We can express all which is beyond the adiabatic correction in this way. As this is has a suggestive form because I'm writing as the temperature times this sigma dot, and this sigma dot is precisely what is interpreted as the rate of entropy production. Why? Because we can quite easily verify that this component, so this adiabatic correction for the flux, describes a reversible process. If we calculate the heat in a process taking place in a given time time interval delta t, we see that we can re-express this integral as a line integral. And this line integral depends on the, doesn't depend on time at the end, but depends only, is a geometric quantity that depends only on the values that these parameters take along the trajectory. So we can define this vector given the different adiabatic coefficients and express the heat in this way. So which precisely tells us that this is a reversible process. So if we have to consider we have to, if we want to consider the heat flux into the reservoir beyond this reversible contribution, we have to go to higher orders in these velocities. And this is perfectly consistent with the fact that this work, which is dissipated, is in fact a bilinear a function of the velocities. So we cannot take into account that dissipation component if we cut the expansion of the flux only at the level of the linear term. So we see that precisely this work, which is dissipated, is the one which contributes to this rate of entropy production, which is a higher order process in the velocities. Okay, so another interesting thing, I'm going to stress it further in a while, is the fact that if you look at this expression, in spite of the fact that these lambdas can have, so this lambda is a matrix or a tensor, and it has asymmetric and symmetric components, but to this bilinear form, only the symmetric component contributes. On another hand, as this is precisely what contains the information of the entropy production, in order to be in agreement with the second law, this quantity must be positive. Okay, so this was very general, so I didn't give you any way to calculate this linear response adiabatic coefficients, but the case of systems which are weakly coupled to the environment are very special, and they are usually treated in the Lindbladian description. So in the usual Lindbladian description, which could be formulated, for example, for the case of the frozen Hamiltonian, we calculate the evolution of the reduced density matrix for the system. I think that there are lectures afterwards which will go more into the details. Johannes mentioned something in this direction yesterday. So we have this equation which rules the evolution for the reduced density matrix, and what usually appears here is a non-time dependent Hamiltonian. So a Hamiltonian, which could be, for instance, this Hamiltonian corresponding to the frozen parameters. Okay, so this equation can be further rephrased in a way, so this is a matrix, this is actually an operator, and this L here is the Lindbladian, is a super operator. But this can be rephrased, as Johannes was explaining yesterday, in terms of, so the matrix elements of this density matrix can be reorganized in the form of a vector. So at the end of the day, we can express this part of the equation in the form of some matrix which multiplies the some vector. We can collect all the matrix elements into a vector, or we can introduce some block representation or something like that, and we can have some expression like a matrix times a vector. So this is the free dynamics, so the dynamics with the free Hamiltonian, and all the information of the coupling to the reservoir is indicated here in this Lindbladian. Okay, so the stationary solution should be found asking that this time derivative is equal to 0, and this looks ugly, looks like a not well-defined equation, but if we introduce also the normalization, we will have an equation, a well-defined linear equation from where we can calculate all the elements of our density matrix. In the form of which are, as I said, collected in that vector. So let's try to see if we can implement in this language this adiabatic decomposition I introduced before. And this was done some time ago at the level of the rates, but it can be also implemented also for the full Lindblad equation and for the full density matrix. So the idea is that we have this, so the equation I wrote before is a usual Lindbladian equation. I insist that what I'm writing here is the Hamiltonian for the frozen parameters. Let's define an identical master equation, but for the full Hamiltonian. And now let's try to solve it. Let's try to solve it. So here, sorry, the Lindbladian will be the same because the coupling to the reservoirs and all that information is the same. So the only difference is that in the previous case, I just considered the frozen Hamiltonian, which is an equilibrium Hamiltonian, while here I'm including everything. So the philosophy is the same as in the adiabatic linear response Kubo-like. The goal is to calculate, so to find, first of all, introduce some splitting for the density matrix, and the goal is to calculate this adiabatic correction. So this can be done just solving the Lindblad equation for the frozen case. So this is what was done here. But now, so Sorry. Yeah. But now, let's try also to include this adiabatic correction, which our aim is to get just stop at something which is proportional to the velocities. Okay, so this is basically to introduce the procedure. Implies basically introducing this splitting in this equation and solving at different powers of these velocities, stopping only at the linear order. And this is a sketch. This is the sketch of the what I already said for the frozen part. Introducing the normalization, we can get some well-defined linear equation from where I can calculate this quantity. Now I introduce this decomposition at the level of the vector representation now. So previously I formulated the idea with the density matrix. Now we are accommodating the density matrix in vectors, so I have to split the vectors. I substitute this expansion in the master equation, and if we stop at the first order in the velocities, we get this linear equation for the steady state. So in the limit where this rho dot is equal to 0. So we get that, and we can then accommodate things. So basically defining the inverse matrix, operating from the left, and we will get this expression for this vector, representing the adiabatic correction of the density matrix, which is proportional to the velocities. Okay? Well, given that, I can do the same calculation as before, and I can get explicit expressions for a system described by a Lindbladian dynamics for the conservative component of the work, for the conservative component of the forces and the corresponding work they do in a given process, and also for the non-conservative or dissipative components. So as you see, it's exactly the same structure. So, but this is a sort of a receipt to calculate this linear response coefficients for a system that is described in terms of a Lindblad equation. Okay, so let's come back to the properties of this tensor or linear response matrix, and these are the following. So as I already mentioned, it's only the symmetric component contributes. It satisfies Onsager relations because they are coming from susceptibilities, which are evaluated with an equilibrium state. And it is positive because it has to be in agreement with the second law. And what is interesting is that it can be also interpreted as the metric of in the parameters space. This is because of basically the property that is symmetric. Only the symmetric component contribute, and it is positive defined. And this is something that has been recently exploded to optimize protocols. So I'm going to explain further. So these properties of this, description of the dissipation were already discussed, as you see, a long time ago, even from people coming from the area of chemistry. But recently, there is a quite active community which is also taking advantage of these properties. What is particularly useful is the fact that it is possible to define this quantity that is given the name of the thermodynamic length. So the thermodynamic length, so as you see, is quite ugly, that we have to compute. So this doesn't look like a geometric quantity, but because at the first sight, because it depends on all the details of the protocol. So it's not something that depends like the reversible component of the heat, that depends only on the different values visited by the protocol, and it can be written as a line integral. Instead, this, because it depends, it's a bilinear function of the two velocities, it depends on all the details of the protocol. But these properties, and in particular this concept of the thermodynamic length, is useful to connect with geometrical quantities, to a geometrical description, and as I said, it is used to optimize cycles. The connection is like this. This is the thermodynamic length, which is basically the square, so it's the same integral as before, but the argument of the integral contains the square root instead of the function we originally had. And what is interesting is that we can use this Cauchy-Schwarz inequality of integrals. So this is Cauchy-Schwarz inequality, and if we put here this function g equal to 1, we can get this, this inequality for the dissipation in terms of this thermodynamic length. And this is what is really useful to find bounds for dissipation. So we see that here we have on this side of the inequality the dissipation, and that this is bigger or equal than this quantity that can be related to geometrical concepts. And this is precisely what is useful to find protocols minimizing dissipation. So this depends on the trajectory, but given this length and given this metric, there is one path that receives the name of geodesic. That is the one that minimizes this thermodynamic length. This is a result of differential geometry. And what has been proved is that the paths that minimize this quantity correspond to the case where this argument of the integral is constant. And the argument of the integral is precisely the rate of generating dissipation. So it's interesting that the result is that if you find some path such that you can circulate it, cover it, generating dissipation at the constant rate, so at the end you get the minimum dissipation for the whole process. Okay, so this is what is exploited. Of course, it is not a useful, it's not completely useful because it's very difficult to find those paths for which you always have this quantity constant. So this is, in general, a difficult problem, but in some cases it can be solved. And this is an example. So this is the example of a qubit. You can look at all the details in this paper. This a qubit where here there are all these control parameters, so it is not, I just copied from the paper, it is not explicitly indicated, but all these coordinates can change in time. The description is precisely a Limbladian description in this case, so this, and it's, the procedure is like this. So this is the Hamiltonian in the lab frame, and the Hamiltonian is diagonalized with some unitary transformation, and it is written the dynamics. It is assumed that the dynamics for the density matrix is given by this Limbladian equation. So this is a typical Limbladian equation, in this case for a single qubit. Okay, so there are things. So these are the rates that describe the contact with the reservoir. That depends on the characteristics of the reservoir. It is here considered the possibility that the reservoir is a reservoir, a caldera-legged-like reservoir, with which can be described by some density of states, which can have some ohmic, supra-ohmic, or sub-ohmic behavior, and this is contained in this exponent alpha. So these are the characteristics of the bath that enters the Limbladian equation. And okay, so in this case, the transformation from the matrix to a vector is quite easy because we have this block representation. So this Lindblad equation can be expressed in this way in terms of these vectors. This is for the steady state, so this gives me the solution for the steady state of the frozen system, and from there we can transform back to the laboratory frame and calculate the adiabatic correction. Given this vector, I can recover the matrix and come to calculate the dissipated power. So the dissipated, this is power, sorry, not work. Okay, so these are some examples. So these are explicit calculation for these Onsager coefficients in this problem, and these are some examples of optimizing the protocols according to the criterion of minimizing the thermodynamic length. What is interesting here is the structure of this Onsager of these linear response coefficients. We can identify one which is purely due to changes in the radius in the Bloch sphere, only changing the amplitude of the. So we can think about this problem as a spin in a magnetic field. If we change just the amplitude of the magnetic field, we just change this parameter R, and this is precisely the dissipation due to slow changes. So this kernel contains the information for the dissipation of slow changes in the amplitude of the magnetic field, and this is identified as a classical component. So we just change the difference of energy in the qubit, if you think in terms of qubit. While all these other terms describes the dissipation due to rotations of the qubit, of the state of the qubit, or the spin. Okay, and you see that these are they behave really quite different. So these are for some chosen protocols. These are the geodesics. So these are the paths corresponding to the minimal dissipation connecting 2 points, and this is a comparison of a naive evolution with an optimal evolution. So you see, naive evolution means that you make any change of your parameters connecting your points. So it's a given random path. And this is the optimal, the orange is the optimal path, and you see that this is something that is meaningful and useful because you could optimize the path in order to minimize the dissipation. So almost finishing, just last comment. So we saw that only the symmetric components of this tensor or matrix containing the adiabatic linear response coefficients contribute to dissipation. But we can ask ourselves what happens with the antisymmetric one. So it can be some system. So in most of the protocols, you just have only a symmetric component. But you can figure out protocols where you also have this antisymmetric component. And which is the meaning of this antisymmetric component? Okay, so there is quite, so there is this work in which this question was formulated, and they gave the name of this antisymmetric component of geometric magnetism. But basically, what you see is that it is some process in which you don't have dissipation. It will have as only the symmetric component contributes to dissipation if you have some protocol that for which you calculate all these adiabatic linear response coefficients, and you get only an antisymmetric component. It will be a process where you have some evolution, you have changes in your system without dissipation. This process leads to what is identified with power pumping, or a process of work conversion. And this was proposed, a process of this type were proposed in this paper, but not in the adiabatic regime, but in a so-called Floquet regime, where you have very rapid changes where plenty of harmonics of your driving fields play a role. But it can also be formulated, and this was with other name what was discussed in this previous paper. This power pumping means that you can define an exchange of power between two driving forces. So imagine that you have two driving forces, and you calculate this quantity, the power that develops one of the forces minus the power developed by the second force. And if this gives you in average, so afterwards we average on time. If this gives you a number, this means that one of the forces will be always giving some work to the other. And precisely this is what is described with this antisymmetric term. So this is not quite explored concept so far, but there are some works. I don't know if I included. Yeah. This is one example, a recent example where they connect this process to topological behavior and so on. So it's something which is under development. I wasn't doubting if including more details or not. So I just give you the idea that these things are under are evolving. So should I finish, or do I have? No, no. I have still one thing to. 15 minutes. Okay. So in 15 minutes, I just comment briefly. So far, the examples I gave were on a system coupled to bosonic baths, to caldera-legged baths. But a few words about dissipation in electron systems. And in electron systems, the simplest system that where you have a small a few level electron system connected to a single reservoir is this one. So it's the so-called quantum capacitor. In quantum capacitor, it's nice because there are several experiments. There are okay, this is a review written by experimentalists, and there is plenty of bibliography there about that problem. This was proposed originally by Luttinger and co-workers some time ago, but it became popular after the experiments. Okay, so it consists in the following. You have a few level electron system with connected to some voltage which changes in time. So it's time dependent and AC voltage actually. And the response of the linear system, so here linear means linear in the amplitude, so it's like a linear circuit where this voltage is small, so we are here linear means that it's linear in the amplitude of the applied voltage. And so this is the frequency at which the voltage oscillates. And the quantity here that relates the energy, the current, the electron current between the capacitor and the reservoir is the admittance, receives the name of admittance in circuits, and it depends on the capacity and the resistance of the circuit. In this problem, it can be seen that the capacitance contains two components, one which is purely quantum and another which is the usual geometric capacitance. And what is interesting is that the resistance is purely quantum, is precisely defined by fundamental numbers by fundamental constants. This is a review of that appeared more or less recently about this problem. It's a very nice review. And this is here you can see how we can get an expression for the admittance in terms of linear response cubo, usual cubo theory. Let's start from this Hamiltonian for the electron system. This is the time-dependent voltage. And in evaluating in linear response, we have the following. So linear response means that we define this admittance like in this way, that at this ratio between the charge accumulated in the capacitor divided by the voltage, and the calculation given that Hamiltonian provides us this charge-charge time-dependent correlation function, or the susceptibility. And from there, we can calculate and get an explicit expression for the admittance. What is used here is the fact that there are these Corringa-Shiba relations. These are Fermi-liquid relations for this interacting system governed by this Hamiltonian. This relation, look, is not the usual fluctuation-dissipation relation, because this is the real part of the susceptibility square. So this is some relation that is not trivial to be proved. You have to rely on Fermi-liquid theory and so on. And from there, you can explicitly get this value for the quantum resistance. Similar thing can be, so similar approach can be done from the point of view of the energetics, and we can use this adiabatic linear response description, in particular for the rate of change. So this is the sketch of the Hamiltonian. I'm not writing here the Hamiltonian, but we are considering here a Coulomb interaction as well as the time-dependent voltage. Here, this is the rate of change of the charge stored in the capacitor, so the charge stored in this system, and this is precisely what defines the current between the time-dependent current. So here the current has a vanishing mean value averaged over time, because we have just one reservoir. But what we are talking about is about the time-dependent current. And we can also calculate the power. So we see that in this problem, which plays the role of the force is precisely this charge. And we have only one time-dependent parameter, which is the gate voltage. This is the adiabatic expansion for this problem, and from there we can calculate the power, just substituting here. So we have the conservative part, which is the linear in the velocity, and we have the dissipative part, which is quadratic in the velocity. In this problem, the evaluation of the adiabatic susceptibility has been done numerically with the numerical renormalization group, and it was these Corringa-Shiba relations were verified, and what it is found is precisely that introducing this quantum of the resistance, you get, introducing in the adiabatic expansion, you get this expression for the dissipated power, which has precisely the form of a Joule law, with which is a quantum Joule law, because we have a quantum of resistance there. Okay, so I'll stop, and yes, sorry. I just leave you with the summary of all the things I was telling you today. So we spoke about the dissipation in a finite time process at slow driving, and we saw that it can be described as a function that is, it can be described in terms of Onsager, of linear response coefficients, which satisfy Onsager relations, and that the dissipation is a bilinear function of the velocities, that only the symmetric component contributes to this description of the dissipation, and because of that, this is some useful property to define metrics and introduce these geometric concepts. And the antisymmetric part describes processes of power pumping without dissipation. Okay, so thank you. Questions?